Good evening, students. My name is Shivacharan. I am working for Sai Krupa High School, Krishnanagar. Today, we are going to discuss about the chapter, very important chapter, Electromagnetic Induction. So, this is a subtopic of electromagnetism lesson. So, the main topic is electromagnetism and the subtopic is electromagnetic induction. So, in this lesson, we are going to learn about the electromagnetic induction. So, in the diagram itself, there is a coil. This is a called coil, and this is the bar magnet, which is the north pole pointing towards the coil. And the arrow marks are showing the direction of motion of magnet. So, in this lesson, we shall learn about the electromagnetic induction. So what is the phenomena here? The phenomena of electromagnetic induction can be demonstrated by an experiment. So in the diagram there is a coil or loop. Now when wind an insulated copper wire on a paper or a wooden cylinder so as to form a coil in the form of solenoid. So it is in the diagram. It is shown in the diagram. So connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is not moving, that is stationary. The pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. So the galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet is keep on moving, the current flows in the solenoid. Is it clear? Now, if the magnet is moved away from the solenoid, then current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. This deflection increases if the magnet is moved away with a greater velocity. So, if the speed is more, the deflection is more. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then current flows in an opposite direction and the galvanometer accordingly turns towards the left. So Faraday observed that the current flows in the coil only when there is a relative motion between the coil and the magnet. So the direction of deflection in the galvanometer is reversed if the direction of motion is reversed. That you have to understand here. So now, the factors leading to the increased current in the coil, let us discuss now. First, how? By using a strong magnet or by increasing the motion of the magnet. And third point is to increase the area or the number of turns in the coil, we can increase the current by these factors. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So the galvanometer shows no deflection. It remains still. But when the magnet is moved towards the coil or vice versa, then the magnetic flux changes and an EMF is introduced or induced in the coil. If the circuit is complete, the EMF causes the current to flow through it. See here, in the position of the magnet when it is at rest here, and so there is no deflection in the galvanometer. The magnet moved towards the coil, deflection in the galvanometer is in one direction. And magnet is held stationary at the same position, then again no deflection in the galvanometer. Magnet moves away from the coil, deflection in the galvanometer but in opposite direction. The magnet is held stationary at the same position which is away from the coil, again there is no deflection. So these are the points you have to remember while doing this kind of experiments. So what is the position of magnet and how is the deflection? Now coming to the topic, Faraday's law of induction. Whenever there is a change in the magnetic flux linked with the coil, an electromotive force is generated. What are the factors affecting the magnitude of EMF? Number 1, change in the magnetic flux. 2, the time in which the flux changes. That means the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. That means the change in the flux occurs in less time big change occurs in the magnetic flux, that too in a less time, then we can say that more induced current is generated. So that is nothing but the magnitude of the induced EMF is directly proportional to rate of change of magnetic flux linked with the coil. So the direction of induced EMF depends on whether there is an increase or decrease in the magnetic flux. So John Ambrose Fleming gave two rules to determine the direction of motion or the direction of induced current, known as famously Fleming rules. Well, the left hand rule is for electric motors and the right hand rule is for generators. According to Fleming's right hand rule, if the thumb, the forefinger and the middle finger of right hand are stretched perpendicularly to each other, then the thumb represents the direction of movement of the conductor and the forefinger represents the direction of magnetic field and the middle finger represents the direction of induced current. It is clear in the diagram. You can observe. Now coming to the Lenz law. Lenz law states that the direction of induced EMF is such that it always tends to oppose the cause which produced it. So when magnet is inserted into the solenoid, a north pole will be induced on the right side of the coil to oppose the incoming north pole. So here we are seeing the north pole. As soon as the current is produced in the clockwise direction, which is shown in the galvanometer right side, there is a north pole is formed. The base of the coil is acting like a north pole and repelling the north pole. So by the right hand grip rule, the induced current will flow anti-clockwise so that the pointer deflects to right. Now by the Lenz law, when the magnet is withdrawn, when it became taken out, it means going in the opposite direction, then a south pole will be induced on the right hand side of the coil to oppose the outgoing north pole. By right hand grip rule, the induced current will now flow clockwise so that the pointer deflects to left. So this is a Lenz law. Now Lenz law obeys Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. More counter force is developed when the speed of the conductor, the magnetic force and conductor size or even conductor conductivity increases. It also obeys the law of conservation of energy. It states that energy can neither be created nor be destroyed. Therefore, the sum of all the energies in the system is constant. You can observe in the flow chart. So changing of magnetic field. Changing of magnetic field goes into the iron core, generates induced EMF. And this is in turn producing the alternating current. And it is again creating the changing of magnetic field again. So because of changing magnetic field only, we got the induced current. And what is the induced current here during producing again? The change in the magnetic field. So mechanical work is done against the opposing force experienced by the moving magnet. And this work is converted into electrical energy as indicated by the induced current flowing in the circuit. Now Lenz law is based on Faraday's law of induction. A coil of wire is moving into the magnetic field is one example of an EMF generated according to Faraday's law. The current induces will create a magnetic field which opposes the buildup of magnetic field in the coil. So here there is a formula. EMF is equals to negative N delta phi by delta T. Means N is here number of turns and phi means magnetic flux and B is external magnetic field and A is the area of magnetic field coil. The minus sign denotes the Lenz law. EMF is the term for generated or induced voltage. Lenz law says that when an EMF is generated by a change in the magnetic flux, according to the Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produced it. This is a statement for Lenz law. Thank you. So whenever there is a change in the magnetic flux linked with the coil, an electromotive force is generated. According to the Faraday's, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So a galvanometer shows no deflection. And the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux linked with the coil. According to the Fleming's right hand rule, if the thumb, the forefinger and the middle finger of right hand are stretched perpendicular to each other, then the thumb represents the direction of motion of the conductor, the forefinger represents the direction of magnetic field, and the middle finger represents the direction of induced current. And Lenz law states that the direction of induced EMF is such that it always tends to oppose the cause which produced it.